opportunities with VLBI transmitters on satellites, and I would like to first acknowledge the co-authors here, Helene Wolf and Lisa Kern from TU Wien and Urs Hugentobler from TU München. Okay, so we have already heard about the Genesis mission by the European Space Agency. The launch is expected for 2028. There will be a lifetime of the operation of 2 years. The orbit will be at about 6,000 kilometers altitude, which is required by VLBI because the satellite has to be visible from at least 2 radio telescopes at the same time. And for the first time, a satellite will be equipped with a dedicated VLBI transmitter. But there is another opportunity or another chance. So there will be a next generation of Galileo satellites. Of course, the altitude is at 23,000 kilometers. And there are plans or ideas to equip some of these satellites with VLBI transmitters in the style of the VLBI transmitter on Genesis. Typically with VLBI, we observe extragalactic radio sources billions of light years away, and our observable is the difference in arrival time of the signals between 2 radio telescopes. Okay, so what are the opportunities? So, of course, one opportunity is that we can determine the orbit of the satellite in the celestial reference frame directly without going via UT1 minus UTC from some VLBI experiments. On the other hand, we can derive VLBI station coordinates from very precise satellite orbits. So we can determine the VLBI station coordinates in the frame realized by these satellite orbits. So these are the 2 opportunities, and I will now show some simulation results. The first simulation is about the estimation of orbital elements of a Galileo satellite. So this is the simulation setup. We have a 24-hour VLBI session with a 12-station VLBI network, and we pick 1 Galileo satellite. And we prepare a schedule, and about 10% of our observations go to the Galileo satellites. We use a 10 seconds on-source time. Then we estimate orbital elements as constant values over 24 hours. We fix quasars and station coordinates. We estimate Earth rotation parameters. And actually, we do a Monte Carlo simulation. The main driver for the Monte Carlo simulation is tropospheric turbulence, but we also simulate clock variation, and we use 10 picoseconds white noise per observation, which is quite optimistic, but I hope not too optimistic. Okay. So this is how the estimates of the orbital parameters look like. And we illustrate here the formal errors and the repeatabilities of the orbital elements from the Monte Carlo simulation. One nice thing about this analysis was that we took the partials that we needed for the Keplerian parameters from the Bernoulli package. It is interesting to see that all Keplerian parameters are converted to units of centimeters. It is interesting to see that the semi-major axis A is well determinable. This is remarkable because typically you cannot get the radial component of Galileo satellites well with VLBI observations. The argument of perigee is difficult to determine, and of course one nice thing is that we can directly estimate the right ascension of the ascending node with VLBI observations. Okay. Estimation of orbital elements of Genesis, this is under development, but in general we expect better results for GNSS because of the improved geometry of the VLBI observations to the GNSS satellite. Okay, then we can determine VLBI station coordinates in the frame of the satellite observed. So why is this interesting? So when we have a very precise satellite orbit, we can derive the VLBI station coordinates. But we can also determine station coordinates from VLBI observations to quasars, and then we can compare the station coordinates in order to assess the frame time. On the other hand, when we derive VLBI station coordinates, but also SLR station coordinates, as we have seen earlier, we can get additional information on the local tie at the sites. In general, I want to emphasize here that it's important not just to observe the satellite, but still to have many observations to quasars. We need those observations for the estimation of troposphere parameters. And in order to illustrate the situation at the ground a bit, I show here the sky plots for Wetzel in 24 hours, assuming one VLBI transmitter on a Galileo satellite at the left-hand side and at the right-hand side on GNSS. And of course, we see the improved situation with the GNSS satellites compared to the Galileo satellite. Okay, now I again show some simulation results. And we focus on station coordinate scatter from 24-hour sessions. We, in principle, have the same simulation set up as shown earlier. And in this scenario, we have 3 Galileo satellites equipped with VLBI transmitters. So we selected 3 Galileo satellites, put a VLBI transmitter on it, and then we did our simulation and analysis. And approximately 30% of our observations go to those Galileo satellites. And the figure here at the lower right side depicts the repeatability, the scatter of the daily station coordinates, and for the east, north, and up components for our 12 VLBI radio telescopes. And we do see here a scatter between 6 and 8 millimeters. So we get very good results with 3 VLBI transmitters on Galileo satellites. There is hardly any improvement with a 4th VLBI transmitter, and if we would only have 1 Galileo satellite equipped with a transmitter, the scatter would be at the 3 centimeter level or worse. Okay, that's the situation for 3 transmitters on Galileo satellites. That's the situation for GNSS. So again, we estimate station coordinates with an NNR condition, and for the estimation of station coordinates, of course, we only use the observations to the satellite and not to the quasar. The quasar observations are just used for troposphere calibration. And approximately 10% of the observations go to the GNSS satellite. Here we do see that the repeatabilities are slightly worse compared to 3 Galileo satellites. We are for the east, north, and up components between 10 and 15 millimeters, but this is not the critical thing, but actually for the GNSS mission, it's important to know how many weeks or how many sessions do we need to observe to get millimeter precision. And now we extended our simulation, and we said we have 1 24-hour VLBI session per week with our 12-station network. And the question is, how many weeks or how many sessions do we need to end up with millimeter accuracy? And we realized this simulation with a stacking of normal equations. So let's first take a look at just 1 station, Wetzel, and what we... Okay, so the first, with the lower light blue arrow, this shows that we only stack the first 10 weeks. Then we stack the first 20 weeks, first 30 weeks, and so forth. And the orange arrow, or the orange marker, depicts the situation when we stack 1 year. And this figure here illustrates the station coordinates of the cell with the up, east, and north component. And we do see that after a year or so, we are getting reasonably close to the expected zero value, to the reference value of the simulation. And sometimes we do see here a significant jump from 40 to 52 sessions, but we check this again, Rolf, and so this seems to be fine. So this is the situation for one station. This is for all stations here. And the interesting thing is the orange dot, because this is the position after 1 year. And of course, we could still say this is driven by tropospheric turbulence. So let's do this 10 times more. So we did the same thing 10 times, and we're only, now we're calculating the scatter of the yearly values. And this is now the simulation result, and we are getting a scatter, a repeatability of the yearly values at the, let's say, 1 or 2 millimeter level in the east, north, and up component, illustrating that there is potential in the Genesis mission for VLBI, for the geodetic variable basal interferometry. Of course, I should say here that the simulation is rather optimistic because no orbit errors are simulated, and currently we use a white noise of 10 picoseconds for our observations, which is also quite optimistic, but I hope that we get reasonably close to these observation errors. So, to sum up, I want to say that VLBI is a useful tool for orbit determination, and it will be very interesting to combine different techniques for orbit combination at the normal equation level. This will be an interesting and important task for the Genesis mission. And so the simulations with Genesis are promising, but of course more realistic scenarios with larger errors have to be made. Thank you.